binary. Let's see. We have a medium today. Small subtree with all the deepest nodes. Given the root of the binary tree, binary is split to 2. The depth of each node is the shortest distance to the root. Okay, sure. Return the smallest subtree such that it contains all the deepest nodes in the original tree. The smallest subtree such that it contains all the deepest nodes. Okay, so if it's like a singleton binary tree, like it's actually what does a binary tree mean? I think it means that there's a left and a right leaf. So if each parent has a single child, then this small subtree might just be the second deepest child. Yeah, so if there is like a okay, yeah, so 4, 7 are the highest depth, and they're common ancestors too. If the 7 was like attached to the 6, then it would go down, it would go up to the 5. 0. 0 goes to 1, 3, 1 goes to 2, so the deepest node tree is 2, solid subtrees are 2, 1, and 0, but the subtree of node 2 is the smallest. I see. So it could be itself if it's the only one at the deepest. Interesting. Okay. So I think so. This is probably gonna be some sort of breadth first search. Breadth first search. BFS. That's probably gonna be necessary. Needed to determine the deepest nodes / level. This breadth first search will go like 3, 5, 1, 6, 2, 0, 8, 7, 4. And then once you have the deepest nodes, then you should iterate upwards until you get a common ancestor. So 7. Yeah, I think so. You go from the deepest nodes, you create for each node of the deepest, you make a list, or maybe a set of its, you make a set of the parents of it, and then you iterate over that until the set reaches 1, in which case you definitely have a singleton common parent ancestor. Okay. I wonder if this can be done using a single recursion rather than using iterative. I don't think you can do a single recursion here. I mean, maybe you can. I'm just not as competent in that. Okay, so let's go ahead and say the current level of nodes is starting with. Should this be a deck? WQ. Last time I did this, I don't think it mattered. So current node is going to be the root node. So while there is a current node, there's a current stack for the node. I think I'll do something like next level is just going to be an empty array. Eventually I'll say the current is going to be put to the next level. Maybe I'll swap this. Current and next level get swapped. No, I don't think that's it. as well. So what happens if this is a singleton? Current, next. Maybe I do something like previous current equals something like that. Because I do need to know, I guess once it reaches the last level, it's going to be empty in the next level. I still need to keep track of the previous. Okay, I think that's right. So next level is going to be actually, this should be a set. Should be list. Nodes at next step. So for every node in the current level, I'm going to do if there is a left side to that node, left child to that node. Next level, next level append. There is a right side. And then I think that's it. And then it iterates until it reaches the end. And then it does the transfer. And then at this point, previous is equal to the last array of leaf nodes. So now I'm going to need to find the common ancestor. So I'll do maybe parents is, let's go this way, while there is something, maybe I'll say current is equal to previous. While there is something in the current, iterate over all these leaf nodes or parents of leaf nodes. So I'll say parents is equal to set for every node in the current. Parents dot add node. Oh shucks. I need to keep track of the parent of each node. This is going to either modify the nodes to actually add that information. Yeah, it's going to need to modify the node to add that information as well. Could also just do a dictionary that maps the dictionary that maps the node to its parents. I wonder. I'll say parent mapping is a default dictionary. I guess it doesn't need to be a default dictionary, it's just to be a dictionary here. Just dictionary or dictionary? I don't think I need parentheses. Actually, maybe I do. Syntax. Parent maps the dictionary. Yeah. There. Use curly braces. Oh, you can set. Okay. Set. Okay. naturally have done sets a bunch, so I remember the sets. Okay, anyway, although I think this is optional. So here I think I need for every node left, it's gonna be a node left. Parent map for node left is equal to the node. I could also just add that information to each node, but I think that might actually store. Yeah, before I forget, I think I need to handle the trivial case. The trivial case is going to be if it is a singleton. It doesn't need to do a thing. If not current, or if not root dot left and not root dot right, return this node. Okay, this is trivial case. Singleton. No. This is going to possibly go to none. Actually, maybe this should break while the length of current is greater than 1. Right, it should stop when you have a singleton ancestor. Singleton parent. Parent. So parents is a set for every node in the current level add to the parent. This needs to be a set because otherwise it might have duplicates. Like 2 children add their same parent to the set rather than to the list because the list would duplicate it. Keep the duplication. Node in current. I think that's fine. And then I think I just say current equals parents. And I think I just return current.pop then. Yeah. Oh boy. Timed out, huh? Alright, see if it goes infinite on. Why would it go infinite here? Current next level, current next level. Let's say print previous. Could go infinite on the first for loop or the second for loop. Probably just another return up there. It's probably going to be infinite in this thing. For each node in current, if while there is a current. Huh. It might go infinite if it's somehow doing some sort of loop. If there's a cycle. Okay, next level is empty for every node in the current level. If there is a left side to the node. Oh my god, what am I doing here? For every node in current, parents not add node. So stupid. Parents not add parent map of the node, which will get the parent of the node. Okay. I think I can remove print here. Hopefully it's somewhat fast enough. Oh, sweet. Okay, cool. So summary, this is 2 parts. First is use breadth first search to get all the nodes, all the leaf nodes in an array. Use a can either use a deck, double-ended queue, or alternating arrays for current and next level of nodes. I use the alternating one here. Also, while going downwards with BFS, keep track of the parents of the, or keep a relationship mapping between child and parent nodes. So I just use a default dictionary, or use a dictionary for that. You can also insert a new field into each node for the parent link, parent reference. Here, after you do that, for each level of nodes, which is starting with leaf nodes, create a set of parent nodes from each. So basically iterate over all those leaf nodes, add their parents to the set using the parent map to identify what the parent node is, and then iterate over those levels until length of level equals 1, which indicates that there is a common ancestor parent. Ancestor parent, which is your answer. Alright, time complexity should be O of n, where n is the number nodes to iterate over. Need to go over each node to determine the leaf nodes using BFS. And similarly to determine the parents. So basic complexity, this should be O of n to keep track of the array of leaf nodes and the sets of parents nodes. And also